Okay. So I don't. If you can help me, what was the formula? We learned a little bit about integration by parts. So let me just give you more examples, and then we hopefully can finalize this chapter somehow. So because the formula that I have it in my head is different here, so I wrote. I think. So let me write integration by parts. So the motivation for the formula integration by parts was that if we can find a suitable formula for calculating the primitive function for the product of two functions, yes? So let me just write, if you see there is a flaw here, just correct me. I think I wrote a capital F of x and then multiplied by g of x minus the integral. And then I remembered that there would be a g prime here. So is this right? Is this exactly what I wrote there or not?
Yes, that's right.
So capital and capital, yes?
Yeah.
Okay, and then we just said that f of x, f is a primitive function for a primitive function of little f. So that is the formula called integration by parts, even though it is not stated in this way in university texts. But I think this is a very nice way of understanding that, because it's a very natural question. We have a formula for the integral of the sum, the integral of the difference. So the natural question is that is there any formula for the integral of the product? When we wanted to explore that, we come up to this one. It is not as useful as the previous formulas because it just reduces an integral to a new integral. So this is always 100% true that this integral can be written in this form, but this is not always useful because it might happen that this second integral is harder to calculate than the original integral. So even though this equality is always true, but it is not always useful. Okay, we solved some of those problems last time. Let me just add some more examples. There are some interesting things going on. Let us discuss about them. So, for example, sometimes we need to do more than one integration by parts. Yes, for example, so let me just do them one by one. So, for example, I ask you to calculate this, the integral. Let me refresh your memory. Let me start with something like this: x squared ln of x dx. Is that mine or that's yours?
Yeah.
Okay. So what can we do here?
Who's calling you?
Who is it your phone or my phone?
Oh, it's mine.
Okay.
No, it's a guy called Mustafa Diriya.
Well, I don't understand what.
I think we should suspend him.
It is on Zoom, you mean?
Yeah, he's been calling people randomly, just like that other guy last year.
Okay. Yeah, okay. But yeah, let us just ignore. So if I want to solve this problem, why I should be motivated to use this formula? Because this is just the product of two functions. Might be this formula is useful. But then you have two options, more or less. You can either choose the first one to be little f and the second one to be little g, or the other way around. What should be in the back of your head is that which choice makes this integral easier to calculate. Okay, sometimes it is easier to choose this one to be f, this one to be g, sometimes the other way around. And I don't think it's that hard. For example, if I want to choose this, the little f, then I need to calculate the capital F. But I don't have the formula for a primitive function for ln of x in my head. So it might happen that I have to go for it, but at least not in the first attempt. So what I will do, I will take this one to be G, and then I will take this one to be F, and see that if this choice is useful. As soon as you decided, you made up your mind, you need to go for it. So what you need to calculate, you need some ingredients for this formula. The first thing is to calculate a capital F of x. So if you say that little f of x is x squared, okay, so immediately you can find immediately one of primitive functions. Capital F is a third of x to the power of 3. Yes? And what more do I need? I need g prime of x. When you tell me that g of x is x ln of x, then this means that, let me just close the door. So g of x is equal to ln of x. I need g prime of x here. So g prime of x is equal to 1 over x, yes? Okay, and I think it's a good idea to call these integrals I so that we don't have to write it again. So this means that I is equal to, I have capital F of x, which is 1/3 x to the power of 3, and then multiplied by g of x, which is ln of x, minus the integral of capital F of x, which is 1/3 of x to the power of 3, multiplied by g prime of x dx. Okay, so now you realize that this was a good choice, because I can write it in this form. I can write 1/3 x to the 3 ln of x, and then I have this x and one of these x's are cancelled. A third, actually 1/3 goes out, then I will have x to the power of 2 dx. But this is easy to calculate, yes? So let me open up space here. So this becomes equal to 1/3 x to the power of 3, and then I have ln of x minus, this becomes 1 over 3, and then this is x to the power of 3 divided by 3. And then, of course, you write a constant at the end. So let me just write the answer. So I is 1/3 of x to the 3 ln of x minus 1 over 9 x to the power of 3 plus the constant c. So, and then you see that we actually did something. It was not easy to guess this function for this this one. Let us check it out again. I want to make sure that everything goes smoothly right. So check. How should I check that? I need to differentiate this function, simplify that, and show that the derivative is equal to this function. Yes, let us do that once. So if I want to differentiate this function, that's a product rule. So let us keep 1/3 here. The derivative of x3 is 3x squared. I multiply it by ln of x plus x to the 3 times the derivative of ln of x, which is 1 over x, minus 1/3 x squared, yes? This becomes x squared ln of x, and then this becomes plus 1/3 x squared, and then I have minus 1/3 x squared, and then you see that this one and that one are gone, and then I get this answer back. So what I did is completely right, yes? But we did it systematically. So this choice was useful, and none of the tricks that you have learned so far will work for it. Only this method. Yeah? So this is powerful. Sometimes we can actually solve this problem using this. But now let me give you a little bit more different examples. So here, sometimes you need to calculate, you need to use the method more than once. For example, if I just give you a simple equation like this, a simple integral, let me call it I again, x squared e to power x dx. Okay, so still we are actually deviating from the main course. We are from main this course, and that was the differential equations. But let us just understand this thing a little bit. So here again, this one, I think you agree with me. This time it is better to take this one to be g, this one to be f of x. Okay, so now immediately what happens? I say that okay. You are telling me that f of x is e to the power of x. I look at my formula to see what ingredients I need. I need capital F and I need g prime. Yes? So I calculate capital F, but this is extremely simple. One of the capital F's is just the function itself. This is the famous e to the power of x function. And the other one, I took it as the gx. So I take it as x squared, and then I need the derivative if you look at the formula. So g prime of x is equal to 2x. Okay? So somebody's knocking?
Yeah.
Okay, sorry. Sorry. Okay, and then we put this in the formula. So what happens? I becomes equal to capital F of x. So capital F, you can leave the door open, Elias, so might be certain of the So I becomes capital F of x times g of x. So capital F of x is e to power x times g of x. It becomes x squared e to power x minus the integral of capital F, which is e to power x, multiplied by g prime of x, which is 2x dx. And then what happens? So this means that I is equal to x squared e to power x, and then 2 goes out, integral x e to power x dx. I would say that this is not, this is actually a triumph, yes. We succeeded to simplify it a little bit, because now I was able to reduce this integral to this integral, but I hope that you agree with me. Definitely this integral is simpler than this original one, because at least I was able to reduce the degree by 1. But what should I do? I need to repeat the process, yes? So for calculating this integral, so let me call this integral this time j. For calculating this, again, I will give the role of g to this function this time, and I will give the role of f to this function. Again, to calculate j, I would say that this time I am taking little f of x to be e to power x. So this gives me that the capital F of x is e to power x itself. And then I know that g of x is x. I need g prime of x. So g prime of x becomes equal to 1. Now what happens? So I have to calculate j now. So j becomes equal to, so forget about everything. I'm just concentrating to calculate j using the formula of integration by parts. So capital F of x is e to power x multiplied by g of x, which is x, minus the integral of the capital F multiplied by g prime dx. But this is simple, because so I would write it in, or so I would write it in this form. But this one doesn't have any role here, so the integral of e to power x is just e to power x. So this is my j, yes. But then what I have to do, I have to take this j and put it into this formula. And then I am able to calculate I, yes? So therefore, I is equal to x squared e to power x minus 2 times, instead of j, I plug this in. So it becomes x e to power x minus e to power x, and then I put a constant at the end if necessary. So then I becomes equal. You see, I can fact this. I have e to the power of x, e to power x, e to power x. So let me just simplify that. I factor e to power x out. So this is an example that shows that sometimes you need to do it more than once to be able to finally calculate your integral. There's also one nice exercise that I want you to learn this trick as well. So let me change this integral to this. This was number 2. Yes, so let us do number 3 now. This is also a little bit tricky. So let me write number 3. I want to calculate this integral. Integral, so let me call it I again. E to the power of x multiplied by sine x dx. I want to find a function whose derivative is the product of these two functions. This is a little bit tricky, so you need to learn this trick. I really enjoyed when I first saw the trick, so it was nice actually. So let us see how it goes. Okay, so here, I don't know, it is not clear what to do. So, but that's a product, so let us hope that we can solve using this formula. So let us take this one to be f of x. Let us take this one to be g of x. Okay, immediately I need to calculate these ingredients, capital F and g prime of x. So f of x is e to power x. So this immediately gives me that. By the way, you can do a little bit better. So let me give a number 2 here as well. So always I am using e to power x. So let me just this time put a factor on top of that. So e to the power of 2x, then what I can calculate, a primitive function for this is half e to power 2x. This. And then g of x, do you want to also put an expression here? Let us just do that and make it nicer. So let us let 3x. Of course, the previous one was easier, but I just wanted to show that there is nothing special about these coefficients. Okay, so let me write g of x is equal to sine 3x. But what I need, according to the formula, I need g prime. Yes, so I differentiate this function. So when I differentiate it, it becomes 3 cosine 3x. That's it. You might see what the problem is, yes? Let us see. I becomes equal to, according to the formula, capital F should be multiplied by little g. So capital F is this one, little g is this one. So let us multiply that. So it becomes 1 over 2 e to the 2x sine 3x, yes? Minus a new integral. Capital F of x is this, multiplied by g prime of x. Let me rewrite it once more simpler. So this I cannot simplify, of course, but here, you see I have a 1 over 2 and I have a 3. I multiply them, that's a constant, I pull it out. Yes, so I got this. But the problem is that, of course, this is a true equality. But if you compare this new integral that emerges with the integral that you have, I hope that you agree with me that they are of the same difficulty. Yes, nothing has changed that much. Here, I have e to power 2x sine function. Here, I have the same e to power 2x, but this time cosine function. Okay, but do you think that it is useful to do it once more on this integral? You might have this impression that this is a circular argument. Yes, what's your idea?
Maybe if we do it again, we can see what the coefficient.
Okay, and then? And somehow it's right, because you might stop here and say that this is useless, because if I do it once more time here, what happens? Cosine goes back to sine, so I will go to my original integral. But there is some nice, interesting thing happening here, so let us explore that, okay? I would say that, yes, it is useful, but see how it is useful. Let me call this new integral j again, and then try to concentrate working on j. So now I will call this integral to be j. And then let us concentrate on j. So j is equal to the integral e to the power of 2x, yes, and then cosine 3x dx. So let us do the same thing. This time, let me choose this one again to be little f, and this one to be little g. And then immediately I need to find capital F, e to power 2x, so the capital F becomes 1 over 2 e to power 2x. Okay, and then of course it doesn't matter which one you choose. I am choosing c equal to constant of integration 0. That's enough. If you choose the other things, then it would give you some extra factors, but constant factors, I think. So then I would say that g of x is equal to cosine 3x, but what I need in the formula is g prime of x. So I differentiate this function, and then hopefully immediately this becomes minus 3 sine 3x. And then I use integration by parts for j, but something interesting happens now. But you also probably was able to see that. We're able to see this. So what happens, capital F times little g, capital F times little g is 1 over 2 e to power 2x cosine 3x. And then you have minus the integral of capital F, which is this function, multiplied by negative 3 sine 3x dx. So this means that j is equal to 1 over 2 e to power 2x cosine 3x. And then this minus 3 times 1 over 2, it becomes minus 3 over 2. I pull it out, it becomes positive 3 over 2. And then something strange happens. At this point, you might think that this is not useful. Because what's happening, it's like a circular argument, yes? To be able to calculate I, you should calculate j, but when you want to calculate j, you need to calculate I. So it seems that it's a circular argument. But do you think it's really a circular argument? So let us see. This implies that j is equal to, let me just repeat this, 1 over 2 e to the power of 2x cosine 3x. And then I hope that you agree that I can write 3 over 2 instead of this combination. I can put I. Do you agree? Yes? But now do you see what's happening? Let me write this one as well. So I would write I is equal to 1 over 2 e to the power of 2x sine 3x. And then this is a minus 3 over 2 j. Yes? So, in order to be able to calculate I need to know j. In order to be able to calculate j, I need to know I. So how can I get out from this loop? What do you think? Yes?
We take the equation for j and then we put it back.
Yeah, we solved. This is a system of 2 equations in 2 unknowns, yes? Here, I have one equation, I have the second equation there. What is unknown here is I and j. So I have 2 unknowns, one of them is I, one of them is j, and I have 2 equations. So I solve that system to find I and j. I is the integral that I need, j is my bonus. I get something extra, I can throw it away if I don't need it, yes? So I can calculate it. So exactly what you are saying, this is not a circular argument, I just want you to understand. I put it back in this equation, so let me call this one number 1, and let me call this number 2. So if I consider number 1 and 2 together, then I am done, more or less. Yes, so this implies that. So what happens? I will have I equals to, I will copy and paste the first part. And then I will have minus 3 over 2, and then instead of j, I will have this expression again. But that's a very nice idea, yes? Because if I ask you what is unknown in this equation for you, you would say the only unknown is I, and I am looking for I. So we can calculate it sometimes in our head, yes? So let us just do it in our head. I need to multiply minus 3 over 2 here. It becomes minus 9 over 4I. I move it to the other side. It becomes, I have one I here. And if I multiply that by that, it becomes minus 9 over 4. I move it here. It becomes positive 9 over 4 times I. And let us see what is left for me here. I have to copy and paste this one. And then I have to multiply minus 3 over 2 by the first factor, which becomes minus 3 over 4 e to the power of 2x cosine 3x. Is that understandable? Yes? And now I add these two together. I have 1i, I have 9 over 4i extra, so it becomes 13 over 4i is equal to that expression. If you want to, I can factor e to power 2x out, so it becomes 1 over 2, 3 sine 3x, minus 3 over 4 cosine 3x, and then I can factor this out, e to the power of 2x. But now I am looking for I, so I multiply everything by 4 over 13, and then let me write it here. So what happens? I becomes 4 over 13 e to power 2x multiplied by 1 over 2 sine 3x minus 3 over 4 cosine 3x. And of course, if you want, you can add a constant at the end. I myself prefer to factor of 1 over 4 out to cancel this 4. So this becomes 1 over 13 e to power 2x. And then it becomes 2 sine 3x minus 3 cosine 3x. That's it, plus a constant. So that was actually a very nice problem, I would say. So sometimes you need to do it 2 times, but it is not like the previous example. It seems to be a circular argument, but if you broaden your perspective, you immediately realize that you can get out of that loop. So that would be the function that we were looking for. Yes? Is that understandable? So more or less, that's a good introduction to integration by parts. Let us go back to the differential equations. So if you remember, we were talking, this came about when we were talking about first order linear differential equations, yes? And I told you that in general, the theory of first order linear differential equations is finalized. We can solve all of them. It might be hard to find integrals here, but in principle, we are done. You remember what was the trick in general? So what was the differential equation that we were looking? We have this method for the case where this is 1. If this is not 1, you have to divide first. So that was the differential equation that we were looking for. And I told you that we have the notion of an integrating factor. Do you remember? We were able to find a factor, mu x, and we also discovered the formula for this integrating factor. It was E, the Euler's number, to the power of integral of this p of x, d of x. And then when you calculate this, you multiply both sides by mu of x, and it turns out that the left-hand side, after being multiplied, can be written as this. And on the right-hand side, you will have mu of x, q of x. And then you integrate both sides. You find the primitive function for this. To be the integral of mu of x, q of x, d of x plus a constant. And then you are looking for y. So y becomes 1 over mu of x times this expression. So in principle, in theory, this is the formula similar to the ABC formula. ABC formula is designed to calculate the roots of a quadratic equation. This is the formula designed for finding the function which is a solution to this linear differential equation. Yes? Okay, so what is the hard part? The hard part here is actually calculating this integral. And the reason that I deviated a little bit about from the main discourse is because most of the time you need integration by parts to be calculate this integral. Yes? So do you remember the logic now? So for calculating this integral, most of the time you need to know integration by parts. And of course, if these two functions are so complicated, my problem will be how to find that. And then I told you that even though I can give you any function, even very complicated, and I ask you to differentiate it, you can always do that. But I cannot always give you a function and I ask you to find a primitive function. You can find a primitive function, but not in terms of the functions that you have already studied. For example, if I ask you, can you give me this? Can you give me a function whose derivative is this? I don't need to make it complicated. Can you give me a function whose derivative is this? Among all the functions that you are familiar with, there are no functions whose derivative is either that one or this one, even though these functions are not complicated at all. So it means that later you will see that people artifact new functions whose derivatives are these functions. And this is tricky. What they do, there is a theorem called first fundamental theorem of calculus. So they define a function. Yes, they define the function in this form. They say from 0 to x, e to power minus t squared dt. This function is reasonable. You might say this seems like a circular argument, but this is not. If I ask you, do you think this makes sense? You would say yes. Why? Because e to power minus t squared, if this is the t-axis and this is the y-axis, I hope that you agree with me, this is a continuous function. And when I increase t, so if I put t equal to 0, it becomes 1. So if you see that the graph of this function would be something like this. Okay? So that would be the graph of e to power minus t2. But what does this measure? 0 is here, x is here. If I ask you what is this integral is this area. Okay, and then what happens if I change x, this area is changing. So this value is a function of x. And by the first theorem of calculus, if I ask you to differentiate this function, you should be able to differentiate functions, yes? Because do you agree that this is a function? It's a function of x, because if I start changing x, the value changes because that value is the area. So what this quantity is, this quantity depends on x. So it's a function of x. And then you can show that if you differentiate this function, it becomes exactly e to power minus x squared. So if I ask you, is there any function in this world whose derivative is this? Yes, that is this function. So do you understand that notion? So we are artifacting new functions. If I ask you, so you shouldn't feel strange. You should feel this is the function. It follows the same definition of a function. You have a quantity which uniquely depends on the value of x. When you start changing x, the value of this function changes correspondingly. So that's a function. So it's a function. And then if you have a function, you can talk about the derivative of that function. And in a little bit more advanced mathematics, you can show that if I calculate the derivative of this function, it becomes exactly this function. Okay, so sorry, I should have put a minus sign here, for example. Okay, so this function is something that we artifact, whose derivative is that one. Yes, so it's a function. Yes, if I want to calculate the function, that I will have the same problem. If I ask you what is f of 2, you have to calculate integral from 0 to 2 of this function. You might say this is why this is hard. Yes, it's the same story. If I ask you what is log of 2. Log of 2, you also face the same problem, yes? So you need to find it in some way. So if the values are hard to calculate, that's not a problem. But that's an artifact. I just want you to understand that it is not possible to choose any function that I like here and I ask you to integrate it. it is always possible if the function is continuous and some kind of properties, it's always possible to at least either we find this primitive function among the famous functions, or if there are no, we have to artifact a new function whose derivative is that. Okay? So what we expect from functions, what we expect is that if I ask you logarithm of x, if I ask you f of x logarithm of x, you consider this as a function. If I say f of x, by the way, equals to sine x, I want you to feed that this is the same scenario. If I ask you f of x is equal to sine x, what is f of, I don't know, 11 pi over 7? So you are facing the same problem, yes? But you need to find some tricks to be able to calculate this. And the same story is here. You need to find some tricks to be able to calculate the value of the function. So that's what I want you to understand. Okay. But there are some famous functions in applications. So for example, this function, the famous applications, especially coming from physics, are some functions, some special functions. Sine and cosine functions are ubiquitous in differential equations from practical purposes. Okay, so for example, I don't have any example in my mind right now for the first linear differential equations, but for the second differential equations, everything is related to, for example, you can cook up a physical system, including a mass and a spring, and then you can push the mass all the time. That term is a periodic function that appears on the right-hand side. Okay, so what I want to say is that even though in theory we finalize the solution of this problem by just one single formula considering all cases, but still calculating this integral might be hard, it is useful to think some alternatives if we can go for them. And I want to teach you the alternatives, and if we finish, hopefully that will be the end of this lesson. So the alternatives is these are alternatives. So Qx, some special cases, I would say, some special cases. So do you remember? Let me compare it with this one. For example, when I write this equation, yes, when I write this equation for you, and then I write the formula minus b plus or minus square root of b squared minus 4ac divided by 2a, is completely generic. But do you really, if I give you this equation, do you really solve it using this? Of course, in principle, you can solve it, yes. A is 2, B is 0, C is 0, but no one goes through this formula, even though it's completely correct. That's the same idea. Yes? Of course, you can solve all these problems using the formula that I got here, but there are some special cases that you can solve the problem a little bit easier. So let us just do that. One of those cases is Qx is a polynomial. So let me start with the simplest case. Qx is an exponential function. Yes. Number two, Q of x is a polynomial. Number three, Q of x is a combination of sine and or cosine functions. Is a combination. If you want to, the terminology is called linear combination. Is a linear combination of sine and or cosine functions. So you understand what is the point. The point is that I don't need any of these special cases because I was able to solve this formula, to solve this differential equation, its full generality. By the way, that formula is not included in Math 5. These three cases are included in Math 5. But I want you to learn both of them. In order to understand that, so what is my purpose? What's my goal? My goal is to solve this differential equation, find the general solution. The general solution should contain one free parameter when I have these cases, yes? So before doing that, I am telling you that this is a linear differential equation, but I haven't talked about what do I mean by linear. I want to teach you now, okay? So why this equation is called linear? This is the meaning of being linear. And it is a very important property which makes the theory of the differential equations much simpler. If you have a linear differential equation, then the theory of that differential equation is simpler. What do I mean by linear? By linear, it means that if you give me two solutions of this differential equation, it's guaranteed that the sum is always a solution. If you give me two solutions for this differential equations, I add them together, I get a new function. This new function is again a solution. If you give me one solution, see this one, and you give me a constant number, if I multiply my constant by this one is again a solution. So if you give me two solutions, if I add them, the answer becomes again a new solution. And if you give me a solution, if I multiply it by any constant that I like to, then I will have a new solution again. But this is easy to prove. Let us prove the first one. You can do the other one yourself. So what I'm saying is that y1 is a solution. So what is the meaning of this? From this sentence, I can conclude that it satisfies my equation. So this means that y1 prime plus p of x, y1 is equal to q of x. Do you agree with that? That is the meaning of being a solution. Okay, so y2 is a solution. So what does it mean? Sorry. Sorry, I made a very big mistake. So this is not linear at all. Okay, so I really messed up. This is linear if qx is 0, and you will see why. Because if I add them term by term, this becomes y1 plus y2 prime. This becomes p of x, that 1y plus y, and then I will have 2qx, not qx. So this is, so sorry, that was, I really messed up, so I should be careful about that. So this is not a linear differential equation, but why we call it linear? It's strange. So from the beginning, the name linear was wrong. It is linear. Yes, it is linear if q of x is equal to 0, sorry. This one is linear, not that one. Okay, so I messed up, completely messed up. So how can I fix it now? Okay. So let me just do it here. So the name was not linear differential equation. So it was first order differential equation. Okay. Okay, so except for that, I didn't mess up anything. So that was right. So the name linear was not actually for this. If this one is not there, then that's linear. Yes. Okay, so what we need to do. This is the point. This is called, by the way, okay, I remember the words now. So this is called non-homogeneous. This is called non-homogeneous. And if q of x is equal to 0, this is called homogeneous. And linear. So let me see if I confuse the names, because oh, they have written first order linear equations. So what I have written was correct. So everything was right. So what I gave the name for this was right according to this book. Yeah, that was actually right. First order linear differential equations. The first order linear differential equation is one of the type. Yes, they name it linear first order linear differential equation. But that is very strange because this doesn't have the linear property. So yes, and anyway, that might be a little bit of misnomer, but this what I called was completely right. So what I did before was right. So this is called linear, first order linear. Differential equation. So that is correct. But we have, on top of that, we have two more terminologies. If Qx is not zero, it is called non-homogeneous. If Qx is zero, it is called homogeneous. Okay, so what I said before was right, completely right. So first order linear differential equation, Qx is not zero, it's called non-homogeneous. Qx is equal to zero, it's called homogeneous. Okay, that's correct. And now my point is to calculate, my point is to determine a general solution for this equation in a different way. What I am trying to motivate is that if you want to find a general solution of this equation, you do it in two steps. You take this away and put zero, okay? And then you solve it, and then what you find, we call it YH, H for homogeneous. And by the way, this is something you can always write in front. What is that answer? We can find it. Do you remember, if you go back what I wrote for you, y was this formula. Do you remember? It was 1 over mu of x integral, what was that? Mu of x times q of x plus a constant. Do you remember? That was the general formula. In the case of homogeneous one, q of x is equal to 0. So this is totally gone. And what is left is c times 1 over mu x. And what was mu x is it's in the board. So I bring it up so it becomes c e to the power of minus integral p of x dx. So you immediately write the formula here. Of course, in the book, it is simpler than that because p of x is a constant in the book always. Okay, and then what you do, you find a particular solution for this, not the whole solution. You solve it, and then you find just one answer. We call it VYP, particular solution. And then what you want to do, you can say that Y, the solution for my differential equation, is the homogeneous part plus the particular part. So this is the theory, an alternative way to do this. Yeah. So what I'm saying is that if you are looking for the general solution of this differential equation, you can do it in this way. You can put this one equal to 0. It becomes a much simpler differential equation. This is 0. Using that general formula, you can always find the general solution of that. If you are lucky in any way, you can guess just one single solution for this, not the whole solution. If you're lucky and you can find one solution of this differential equation, let us call it y particular. Then if you add this solution to that solution, you get a general solution of your differential equation that you are interested in. Okay, so it might be I have confused you. Let me clean this. I will write it again. But let me give you an example here. It would be very good if I give you an example from the previous lesson. I don't know. Can I see one of the previous examples? Do you have it with you here? One of the simple ones that we can solve here. Yes, let me take this one. What was the general? Can I see the solution at the end? What is the solution? Oh, this is, where is the final solution? Oh, yes, that is x. Okay.
X minus 1 plus.
Okay. So let me just take this one. So, for example, do you remember we solved this before? Okay. So we solved this in the previous session. But to understand what that method is, let us solve this using this method. Even though it is very artificial, but it is an alternative way. From theoretical point of view, it's very important. So do you agree that this is a linear differential equation because it fits to the format of a linear differential equation, but it is non-homogeneous, yes? Because the right-hand side is not 0. So it's a non-homogeneous differential equation. This method tells you that you need to divide this differential equation into two pieces. One, concentrate on the homogeneous part. And solve this one. For the homogeneous part, we have a very compact formula. It's very nice, yes? So what is P of x in this problem? So P of x in this problem is 1. Qx in this problem is just x. So what I have to do, I solve this one and find the homogeneous one. For the homogeneous one, I have a formula. It's a constant, e to the power of minus integral of p, which is 1, dx. But this becomes y homogeneous is equal to c e to the power of minus x. Because the primitive function for 1 is x, there is a negative sign behind that, it becomes this. So this is all possible solutions, actually. But if I want to find a particular solution, then either I should be very smart to guess, or there are some methods that we want to discuss right now. Okay, you might be able to guess an answer for this by educated guess, but assume that you cannot guess. What type of function do you expect y to be? For example, do you expect that in y sine x appears? It's not, yes? You are not, because if there is a sine x in the function, its derivative becomes cosine. If you add them, there is no reason that I can get x out of it. Might be you can cook up with a very complicated function so that when you differentiate, many terms cancel out and then you get an x. But that is not optimistic. So I would say that the function that I might expect is a polynomial. Yes? And that polynomial should be of first degree probably. Yes? So let us consider a polynomial of this, and I will call it y particular. And these coefficients are undetermined yet. So this is the method of undetermined coefficients. I plug this back into my equation. So what happens? This gives me yp prime is a. I put them back into this equation. So this becomes a plus, instead of y, I put ax plus b, and this is equal to x. And then I will write it in a standard form. I have a polynomial of degree 1, and a and b are constant. This becomes equal to x. So now what I need to do, I need to fine-tune a and b in a way that this polynomial on the left matches with this polynomial on the right for all possible choices of a and b. Yes? For all possible choices of x, sorry. So this is clear. The coefficient of x should be equal to the coefficient of x. The constant term should be equal to the constant term on the right, but the constant term on the right is 0. So you see, there is no guesswork involved except the general form. I guessed the general form, but I didn't guess the details of the general form. I'm calculating those details. So here I get a is equal to 1, b is equal to minus 1. So if I ask you what is y particular, you would say y particular is x minus 1. Now, according to this recipe, the solution, the general solution for my differential equation, so let me write it here. So that it is equal to y homogeneous, the general homogeneous plus y particular. But y homogeneous is this function, and y particular is that function. And I think if you check it with the solution of the previous session, you will see that that's exactly the same thing. So you might say, what is the benefit? You see that heavy integration is not involved. We didn't do any integration, hard integrations. The integration we did was this one. You see, in this method, I didn't even do one hard integration. The only integration involved in this problem was this case. So I didn't need to use integration by parts or whatever. So what I want to tell you is that if this px is a constant number, you might say that still this p of x might be involved, a little bit hard, so I agree with you, it might be hard. But if p of x is a constant number, this integral is also super simple, because if it's a constant number, the integral of a constant is that constant times x. So if p of x is a constant number, this method, I would say, is superior to the old method that you have to multiply and you have to calculate hard integrals, yes? So what I'm saying is that whenever you want to solve a problem, non-homogeneous one, where this p of x is a constant, it is better to use this method by these educated guesses, yes? This would be better. So let me give you some kind of examples here. But of course, if this is polynomial, this is a good guess for your particular solution. If this is an exponential function, for example, let me ask you this. If I give you this differential equation, y prime plus 3y equals to 5e to the power of minus 3x. This one. You see, if I want to solve that one, I would also probably use this method of undetermined coefficients, because what is YH in this problem? YH, according to that formula, is a constant. E to the power of minus integral P of x is a constant here. So this is done. This is super simple. It's a constant. So this becomes e to the power of minus 3x. So this is the hardest integral that we have to calculate in this method. But I need to guess something. I need to guess something for this integral. So so that is the most unlucky example that I brought. Let me make it -2. Okay. Yes. So yp. What do I guess? What is your guess about the particular solution? Can you guess a function, the type of the function, the form of the function, that if you put it here, it might be reasonable to get this answer out of calculations. So what type of function do you expect? By the way, I think I remember, this is called the Ansatz. Ansatz is a German word, okay? So the form of the function that looks right for this is called the ansatz. So you put it there and you determine the undetermined coefficients. So what is yp? Is it reasonable to say ax plus b in this case? No, because the derivative of this will never give you exponential function. Is it reasonable to guess sine function? No. The only reasonable function is the exponential function itself. But do you think it is reasonable to guess something like this? No, because this -7, this is -2, yes? So the most reasonable guess is a constant, which I don't know, multiplied by e to the power of -2x. This is the ansatz. So then we calculate and put it back here because there is still an undetermined coefficient going on. We need to determine that one. So we calculate this, it becomes a -2a e to power -2x. And then I plug it back into this equation. So it becomes -2a e to power -2x, and then plus 3. Yes? Then I have e to the power -2x is equal to 5 e to power -2x. Agree? Then I divide everything by e to power -2x. So it becomes -2a plus 3 is equal to 5. I move 3 to the left, and I calculate a, finally. It becomes -1. And then I am done because I put it back here, and then I find my yp. Yp is minus e to power minus. So you see, this is what I'm saying. The hard part is not to guess the form of the function. The hard part is to fine-tune this coefficient. For fine-tuning this coefficient, I am not guessing. I am calculating. Yes? That's the point. And when you calculate a to the power -1, you put it back. This is your yp, and this is your yh. So you need to remember that when you want to calculate, it becomes yh plus yp, which becomes c to the power of minus. There's something wrong. Yes, I calculated. Yeah, that's correct. That's correct. -3x minus e to the power of -2x. Yes, so that is the general solution of that differential equation. So is that understandable? So that's the method. For example, let us solve one more problem and then more or less we are done. So if I ask you to solve this, I just want you to understand what happens if you wanted to solve this problem. For example, let me give you this. We have y prime minus 5y is equal to, so let us say 3 cosine 2x. Okay, so because this is going to be the last example, so let me tell you exactly again. So assume that you don't know this method of undetermined coefficients. So if you want to solve it using the previous method, what you need to do, previous method, is to calculate mu of x first, which is easy. There is a formula for that. So this becomes e to the power of integral -5 dx. So it becomes e to the power of -5x. Yes? You remember? This was mu x. And then I told you what to do. You need to multiply both sides by this. The left-hand side becomes, at the end, it becomes this. Then I have to multiply that. Do you agree? And then I need to integrate this. So it becomes 3 integral e to the power of -5x cosine 2x dx plus a constant. Okay, so if I want to, I don't want to continue anymore. If I want to continue, do you remember I had a big trouble? Do you remember that was similar to the example that was a circular argument? You see, I had to do a lot of things to be able to calculate this integral. But of course, if I go through that, then I am done. I divide by this and I find y. But because this coefficient is a constant coefficient, if I myself want to solve this and I don't remember the formula for this integral, then definitely I will use this method of undetermined coefficients. So how should I do that? I will follow this rule. First of all, I divide the problem into the homogeneous part. So number one, I would write y prime minus 5y equals to 0. So if you go and see the formula that I wrote, so YH, I know the formula, so let me write it. So YH is equal to a constant e to the power of minus integral of minus 5 dx. So this becomes c e to the power of 5x. As simple as that. So that is the hardest integral that I am involved in. But can you tell me now, the hard part of this method is to find yp, not finding yh. Finding yp is harder here. So it means that I need to have an ansatz for the particular solution. What type of functions do you think will be involved, might be involved, so that it will give me this combination on the right-hand side when I have this?
A sine function.
Not only a sine, because sine goes to cosine, cosine goes to sine, yes? So if I have a combination of sine and cosine, still I have the chance to get cosine, because they might cancel out, yes? So the ansatz here is to say a sine, but there is no point for writing 5x, because the argument is there is 2x, yes? So it is clear that I should write a sine 2x plus another coefficient cosine 2x. Of course, you might say that this method is also lengthy, but you need to go home and do these two from scratch yourself, and to see that this integral is actually more messy to calculate than this method. So here, the good point is that if you are weak in integration, you really don't need to integrate harder than this one. So you just calculate the derivative here. So this is superior, I would say sometimes, because calculating derivatives are more straightforward than calculating integrals. So this I calculate, 2 goes out, this becomes cosine 2x, and then this 2 goes out with negative sign. That's it. And then what I do, I put these two into the original equation. Y prime is this expression. And minus 5 times y. So it becomes minus 5a sine 2x minus 5b cosine 2x is equal to 3 cosine 2x. That's it. Now fine-tuning a and b are simple, yes? Because you see here, I can factor cosine 2x out. I can factor a sine 2x out. On the right-hand side, I will have 3 cosine 2x. Yes, is that understandable? So this is my ansatz. So polynomial functions, exponential functions, sine and cosine functions are among the famous functions that you can have an educated guess for the particular solution. So I guess that this might work. Now I am trying to see if this really works. So it means that I calculate y prime. I already have my y. I put them back into my original equation and try to fine-tune a and b so that this will work. I made a mistake here. There is an a I am missing here. This is a. So 2a minus 2a minus 5b cosine, yes, and then, yeah, that's correct. And now what I can do, I want to make the left-hand side identical with the right-hand side. So it means that the coefficient of cosine should be equal to the coefficient of cosine. And the coefficient of sine should be equal to the coefficient of sine, but there is no coefficient, there is no sine, so that should be 0. So you see, the only guess that I made is this guess, which was not hard. The hard part is to fine tune A and B. I am not guessing them, I am calculating them. So if you calculate this system, if you solve this system, you can find A and B. So for example, I can multiply this by -5, this by 2. So this becomes 4A minus 10B is equal to 6. And then this becomes 10B at plus 25 equals 8 is equal to 0. And then I add them. So 29A becomes equal to 6. So A becomes 6 over 29. You see, it was not easy to guess this number. I didn't guess it, I just calculated it. And then when I found this A, I put it back in some of these equations and I calculate B. So B, let me calculate it in my head here. So if I multiply that number by 5, so it is 30, and I divide it by 2, so it becomes 15 divided by 29. So I think it should be negative, yes, yes, that's B. And then what I do, the last step is to write my y is equal to the homogeneous part plus this particular part. But the particular part A is 6 over 29 sine 2x minus 15 over 29 sine 2x. And this is your general solution. You might think that this is also a tedious method. I'm not saying that's very short, but compared to calculating this integral, first of all, I would say it's a little bit shorter. And it is easier because calculating integrals could be sometimes you need to be very creative. But for guessing and calculating the derivatives, you don't need to be creative at all. So this is also an alternative way. So this is the only way produced, given in the book. But now you have actually a little bit more knowledge about that. So you know that in general, we can solve a linear differential equation in all circumstances. And then you understand the notion of the integrating factor. So you don't need to bind yourself for constants. You can solve it in general, so as we did before. Okay? Any questions? No? Okay, so that is also the last session of Math 5, because next week...
I have a question as well.
Yes, please. Yes, Alex?
Remember the formula you gave for the antiderivative of two products?
Yes.
Who are functions?
Yes.
Could you write it again? I want to see if I wrote it correctly.
So yeah, you cannot rely on my memory for this formula, but yes, we can. Yeah, I remember it right now because. Yeah, so this becomes capital F g of x by minus integral of f of x multiplied by g prime of x dx. Yes. I don't know. I wrote it with red. Do you see it?
Yeah.
So that is the
problem is I'm trying to find it online and I can't.
No, this formula, the way that I wrote it here, this is the reason that I doesn't have it in my memory. This is not exactly very famous, but I really like it, and because the motivation of this formula is clear. If you just write integration by parts, I don't think that you have a chance to get this formula on the web. You will get this formula on the web. For integration by parts, you see that it is called UdV is equal to UV minus integral VdU. So if you just type on the web, this is what you get, okay? That's essentially the same thing. But here at this level, I prefer to use this one because the question is more natural So is there any formula for the integral of the product? Even though it's not a formula because it just reduces an integral to a new integral. But yes, I think this is good to have it in this formula. But later in the university, probably you will see that these two formulas are completely equivalent. They're exactly the same thing.
How would you prove that
This we proved last session.
that's great?
This we proved last session.
That's why. Okay, I was noticing.
Okay, so if you go back and watch the video, you will see how we prove this formula. Essentially, you need to differentiate the right-hand side and show that the derivative of the right-hand side is equal to f of x times g of x. It is not hard. Just go and watch the video. At some point, you will see that. Yes. Okay, thank you very much. So we end the meeting now, and this was the last session for our Math 5 course. Thank you.
I think the only trouble is taking